Hello. Okay, cool. Seems like this works. So, hello and welcome back to Building a Recommender, a live stream series where I show you how to create a basic recommendation algorithm. And so the reason I'm doing this is just to publicly build something that I'm sort of working on in private. So this kind of recommendation algorithm does have a use case, which is the point of me saying that. So basically, where we're at is I've got a synthetic house recommendation data set, which is like a fake real estate data set that I've created. I've got latitude, longitude, house type, price, bedrooms, bathrooms, neighborhood quality, house condition, crime rate, garden size, and house keywords, which is basically pretend LLM data that's extracted keywords from comments. Okay, so what I've done already, I've created a function to get the distance, and then we can use that as a feature. I've also created a filter algorithm, or it's not really an algorithm, but basically in the last stream I showed how easy it is to use a NumPy mask, a Boolean mask, to do filtering on a data set. And by using this mask here, you can do the filtering faster, and it also, in some ways, it is easier to read. I could put like a little comment by each of these and say what they're doing, but it's pretty obvious, right? Like house data, bedrooms has to be less than or equal to the user vector max bedrooms. I think that's doesn't really need explanation. So I got to the point where I'm going to run it, prun cumulative, and the first part, the filtering part, takes 14 milliseconds. The reason I'm profiling the code is because it's important to me that the code runs quickly, because this is intended for a real world application where it does make a difference how fast a response comes in. So, you know, if it takes a second to answer, then that might be slightly unresponsive for a user. And if you've got many requests coming in and each of them is a second, you could see how that can back up a lot. So one of the parts of all of this is trying to do this recommendation quickly, which is also why it's basic, because that's normally faster. So what I'm going to show you today is how to normalize the price column, or say take any continuous variable, normalize it, and then use that as input to a feature. So let's what have I got here? Filtering on house price. Okay, so this is actually very simple, really. So basically, it's just going to be house data price. We've got this. I think if I dot norm, does that work? No. Okay, let's see if there's a version that can do this. That's saying turn it into a normal distribution, but that's not really what I want. Normalize, I'm just going to basically... It basically just means this. Divide equals... Oops. do it this way instead. So basically, when I say normalize, I mean take the largest value and divide every other value by that, and then use that to get everything. That when you do that, you get all the prices on a scale from 0 to 1. Although actually, now I come to think of it, the minimum price isn't going to be 0, is it? So let's do this part first. Bracket this. Nice. So basically what I've done there is said that actually the house price is not going to be, so say you've got min value is like 200,000 or something. So you filter and say, I want houses that are between £100,000 and £200,000. If I normalize by £200,000, the minimum value, the actual minimum, is going to be 0.5, which means even if a house is at the very bottom end of the minimum price, it's still going to have a value of 0.5 instead of 0. So I've changed that. So if you take away the minimum price of a house from all of them, then it starts at 0 and goes up to some max value or whatever. But that is a better normalization because you're using the full range of 0 to 1. Because the max price is, oh, actually, now I come to think of it, that's actually not right, is it? Because this should be, okay, let's call it shifted house data. Oops, don't have to do that anymore, do I? Cool. Then if we say zero, nice. And what about max? Cool, that's what I want. And as we're profiling everything, let's just see how long this takes. 0.004 seconds. Okay, what about just that? 0.002 seconds. Okay, that's nice. So 2 milliseconds we're burning there doing that. Yeah, and so basically this is just a feature now. So I'm going to turn this into a function and say def normalise price. Or actually, let's call it normalize feature. So this is another part of writing code. So if you're a data scientist and you're not really a coder, when you write code, you should always write it to try and be reusable. So if I said normalize price, that's something very specific, and I could be really specific and say, yeah, normalize price, and I'm going to hard code in that it's going to just work on price. But you could imagine I might want to normalize other features in the future. So if I do want to normalize other features in the future, then why not do this instead, where I'm going to say normalize a feature instead, and I can just give the column I actually want to normalize as a parameter. So let's assign the types. Actually, what did I do up here? I think I did actually say df, didn't I? Yeah. extra. Okay. Yeah. Yeah. So let's change this. Cool. And you can actually see that, say I had negative values in my continuous feature, then if I did minus the minimum value, then it's going to be minus a negative, and it puts everything in positive, and you still get the good normalization. So df shifted. We can just put that down here. And I can say, rather than assign a variable, I can say return this dot values. Okay. Now, just check that works. Whoops. Okay, so it's a 4 millisecond-ish function. Roughly 4 milliseconds. Okay. And that's on a, a large data set. What if it was on... So that's it. This is basically, I'm saying that it takes roughly 4 milliseconds for 30,000 rows. But what about for, if I said the first 5,000 rows? How long would that be? Oh, it's the same. Yeah, not much slower, is it really? Okay, whatever. Kill that. All good. Yeah. So now I'll show you something that I like to do. And you will have seen it before if you watch the other live streams, but one of the great things that ChatGPT can do is write doc strings for you, because it's very good at understanding what... Oh, oh no. It's annoying. Sometimes I forget to press shift. Right, there we go. Because it's very good at analyzing your function logically and like figuring out what it is that you want to do. And it's much faster at writing doc strings about obvious things than you are. And then you can just copy it, paste it, normalize, and then read it. Normalize a specified column at data frame. And value becomes 0 and the maximum value becomes RON. Rate of values. Yep. And you can see it, it doesn't really obey PEP8 very well, but it tries. Just check. Still good. Cool. All right, nice. Yeah. So how would you use this how would you actually use this in a recommendation algorithm? So I will just quickly go to here. Oh, why is it doing that? Sorry, 1 second. What's this one? Okay, cool. Hello, 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 hello. Okay. Nice. Nice. So now I'm just going to quickly, yes, I remembered why I did that now. So I'm just going to quickly find the correct thing. Yeah. So wait a minute. Nope, that's not the correct thing. Oh, no. Was it this one? Apologies. Oh, yeah. Okay. I wanted to find a previous algorithm that I had which told me how to create a basic recommender, but I can't find it for some reason. So instead, I'll just show you how I got it in the first place. So basically, this is how I looked it up before, and it is something like addition and then using various functions, etc. It's a bit annoying that I can't find it because it was quite good, really. Yeah, thanks. Yeah, normalise. So this is what I had to do before. Basically, it did the similar thing before where it said, oh yeah, just use a linear timesing to rank them, and that is possible. You could do that, but when I'm working in a recommender, I don't necessarily want it to be, I don't know. It's a difficult one. It could be, but yeah, the transform weight. So exponential weight transformation. What differences? So you could do it like this, for example, where the weighting is going to make a big difference. And I can then set this up to say, okay, well, how much of a big difference do I want it to make? If that makes sense. Okay, so let me show you two examples. So let's say the user wait for price equals, I don't know, 5 or something. Okay, so this is easy enough. This is just like a transformation where I'm saying multiply the normalized feature by 5, and that is the part of the ranking that is represented by price in the house data. That's like how much weight is given to price. And if you do this in a linear way, as in you just have your weight, multiply it by the normalized feature value, then you can just do weight times normalized feature value plus weight times other normalized feature value, etc., etc., and then they all add up to some final ranking that you can use to rank everything and say, oh, this is the one that's most important, this is the one that's least important, etc. But I tend to find personally that some things don't follow that distribution, if that makes sense. Like my interest in a property, in a real estate property, is probably not going to be half as great if it's say I'm happy to go, I'm happy to be in this area and I want to be within 20 miles. Well, if there's a property at 0 miles and it's right where I want it to be and it's got all the other features that I'm interested in, and there's the same property that's out at, I don't know, say 9 miles, am I going to be 9 times less interested? I don't know. Like, that's a difficult thing to sort of quantify. And it's better, I think, to say there's a base level of interest. I'm obviously interested a little bit. And I get progressively more and more interested as I get closer. Not it's like a straight line up or down. But then again, I mean, maybe it's not too bad. This is how I like to think about things like this. So, if I say x equals y or something, yeah, so no. This is one way of thinking of it, right? So I've got w equals 1, my weight, and I could say y equals xw. So that's my actual feature value. So if I've got like 0.1 or whatever, then I'm saying the part of the ranking that is related to price, for example, is 1 times the normalized price value. So I get 0.1. But if I say the weight is 10, then if I have a price value of 0.1, then now it's going up to 1 is the contribution to the ranking. Now this probably makes a bit more sense. If I say plus z, I don't know, t, maybe I can say w2. Yeah, slide for w2. I call this w1. Okay. And if slide for z, if I say that the z value is something, z value is what's another thing I've got? Z value is the distance, say. Then I can say, okay, my Z value for distance is 0.4. But I care a lot about distance, and so actually, no, you can't really see that very well, can you? Anyway, basically what I'm trying to say is you end up with a graph Not sure if I explained this in the best way. Let's try and get a 3D one. Okay, I think that makes a bit more sense now. So what I'm saying is we're interested in this, not quadrant, but octant or whatever. Basically this section of the graph where x is positive and y is positive. And I'm saying that going from 0 to 1, because they're normalized, this area here, if y is price, and I think price is more important, I can give it a greater value, and you can see this plane shift. And what that's saying is, because y is important, this increases in, because y is important, because price is more important to me, because I've given it a higher weighting. As I move up y, if I move along the y-axis, so price gets closer to a higher value for whatever reason, but let's say it's lower, price goes to a lower value, I'm becoming more and more interested. Like the ranking is higher and higher and higher. And then that gives a ranking score that I can use to put against each property and say, okay, this property, based on the contributing factors that we have, based on the user vector, this property has the highest ranking, and therefore we believe it's the one you're most interested in. And then a user could play with like the sliders to change that, and then they could end up with the properties they're actually most interested in seeing. And what I'm saying is you could do it in this linear way, or I could do something like this where I say, actually, the weight's more complicated. It's like e to the power of w1 to the x or something. Which is a bit weird. I don't know why that's doing that. Oh, I guess because, yeah, it has to cross at 1 because e can't be anything less than that. So anyway, whatever. So this is what I'm trying to control, is the shape of this function. And I'm trying to let the user parameterize this kind of plane, this kind of the red thing here. So yeah, hopefully that's clear. I'm not sure if it is clear, but this is how you can think about designing a basic recommender, a basic ranking algorithm, by creating a function like this in many dimensions. I wonder if there's like if anyone knows of someone who's described this better than me, link it in the comments and I'll direct you to that instead. But yeah, that's that. That's how you make a continuous, that's how you normalize a continuous value and turn it into a feature, which can be used in a ranking. And this is a linear ranking, and I may as well show you a exponential ranking. So user weight for price, like I say, ranking is equal to price times the same thing. But instead, I say do that instead. Cool. May as well profile this just to see how long this takes. In each case, 5 milliseconds. Okay. Well, let's run it a few times. A short amount of time. Okay, what about this one? I mean, similar. So apparently doing the extra NumPy exponential call isn't really a limiting factor. So yeah, that's fine. That's good. So we're free to choose whichever one we want. Okay, cool. So in the next one, in the next live stream, I will be showing you how to turn something like this, an ordinal categorical feature. So a categorical feature that has an order into a numerical feature so that we can use it in this like feature extraction thing. Maybe I'll look more into what I was trying to say and explain it better. Okay, chat to you in a bit. Bye.